Okay, we move on to section B 1.5, where we will discuss the main results of charged cosmic ray observations and some of the interpretations. So there will be two parts on this, roughly separating the part or the observations which deal with energies below the Ni energy, so a few times 10 to the 15 electron volts. And then we will discuss separately some of the results which are obtained mainly with air shower. That's simply because the results are very different quality. The literature that I'm drawing upon is listed here. So these are two papers which were published in the Annual Review of Astronomy and Astrophysics in 2007 and in 2015. The paper in 2007 is also available through this archive number which I present here, whereas the 2015 paper is unfortunately behind the paywall, so if you want to access it, you need to be connected to university domain. And then I also list here the paper, not the paper, but the textbook by Malcolm Longair, High Energy Astrophysics, where some of the discussions that I have here actually done in a very similar way. So let's start out with the chemical composition. We had seen already in a previous section where we discussed the main characteristics of cosmic rays, that roughly speaking, the cosmic ray composition follows the composition of the interstellar medium, that is the gaseous material that is between the stellar systems in the galactic plane. And that material is made up mainly of hydrogen and helium and heavy elements which are produced in the stellar cycle. Now, what I show now here is a plot where we have the chemical composition as a function of the charge number. And it's plotted in relative abundance, which is normalized, as you can see here, to some value of a heavy element. So this absolute scale doesn't really matter. It's just the relative abundance that really matters. And note that this scale on the y-axis goes over 12 orders of magnitude. And the x-scale is just the charge number up to heavy elements beyond iron. And there's two graphs. The blue one is the abundance that we measure typically in the vicinity of the solar system. And the black one is the abundance that we measure in galactic or in charged cosmic rays. This is energy integrated. So this goes for several hundred MeV, GeV energies in terms of kinetic energy, integrated up to higher energies. So this is, if you think about it, not resolved over energy, but just integrated over energy, which is of course dominated by the low energy part of the cosmic ray energy spectrum. Now, if you compare the two graphs, you find that for many of the species, like for example carbon, nitrogen, and oxygen, the abundances are very, very similar. And you find that the actual shape is very similar, and also the relative abundance of these three species among each other is similar, just with a slight difference in the oxygen. You find that for most of the species up to almost close to the iron, you will find also very similar numbers. So silicon is very similar, neon argon is very similar, and so on and so forth. You also find a similar shape in terms of helium and hydrogen, even though there's slightly less hydrogen apparently than helium. But if you shift these two curves, you basically would see that the relative abundance is about, again, the same. There's, however, also noteworthy differences. So if you look, for example, these three elements which are just short of the carbon, nitrogen, oxygen, so this is lithium, beryllium, and boron, you find that these three species are very, very underabundant in the interstellar medium. And that's why you need this very huge ratio here. So if you look at it, essentially there's a difference between the relative abundance of lithium, beryllium, and boron in the galactic cosmic rays, which is of the order of almost 1 million times for beryllium as an example. So that means that there's some mechanism which produces somehow lithium, beryllium, and boron in cosmic rays which are not present when the particles are being ejected, accelerated, and become cosmic rays. Whereas the cosmic rays seem to be otherwise following fairly much this interstellar medium abundance. You find also a similar type of feature just shy of the iron. So this group here, this is titanium, scandium, and so on, which is also overabundant, not as dramatically as you notice here. This is just about a factor of 1,000. Then in the case of lithium, beryllium, boron. So these light elements are produced. Now let's start discussing this in terms of what could be the origin of this. You could of course always assume that there's somehow an environment and where the cosmic rays are initially accelerated and injected to become cosmic rays, that this is somehow having a larger abundance of lithium, beryllium, boron than it's present in the otherwise typical interstellar medium. This seems a bit unlikely and difficult to understand because these three elements have a low abundance for a good reason. The reason being is that they are usually not produced in the stellar fusion cycles. Lithium, beryllium, boron are produced, but they're also being used again for higher charge number species which are produced. So roughly speaking, stars do not create lithium, beryllium, boron. The abundance that we measure here is pretty much the primordial one. That is the one that was produced during Big Bang nucleosynthesis, which we will revisit later on. So there's no really easy source-dependent explanation for this overabundance. So there's, however, a much more natural explanation, which basically gives us a very good description of this. So let's assume that you have carbon, nitrogen, oxygen interacting with the interstellar medium. So you have the relativistic carbon, for example, which will hit inelastic or do an inelastic scattering process with the gas, and therefore will then produce a residual remnant of the carbon, which will be probably containing some fraction in lithium, beryllium, and boron. The same with nitrogen and oxygen. So if you deplete a little bit of these three elements, you basically end up having, through spallation, a naturally produced overabundance of these elements here. Let's do it a little bit more quantitatively. So we can do this in a very simple model. And this simple model is oversimplified. So mind you, this is not how we actually describe cosmic ray propagation in the galaxy. However, this gives us a good idea whether this assumption of spallation is or this hypothesis of spallation is a good one. So let's start out basically coming up with some hypothesis. So we say spallation of cosmic rays produce lithium, beryllium, and boron. So that's our hypothesis. And the very simple model that we're going to do is just a so-called one slab model. So let's assume we make a very simple type of picture. So this is now some kind of, homogeneous material, which is between us as the observer and the sources. So let's store the source on the right side. Sorry, this has got to be. So this is the source. And we are the observer on the other side of the slab. So the source will produce cosmic rays. They are being injected, and so they pass through this one slab. So some of them will just basically pass through without any interaction, and some others they will interact here. So we'll have some interaction process here, and then you basically produce some other particles coming out. So that's a very simple model. Let's assume now that this is a one slab model. That our one slab of matter is homogeneous, so we have a homogeneous density. So the mass density should be rho. And let's assume that the path length, so the distance through which the matter, the cosmic rays pass, has a thickness of s. Then we can basically say that the psi value, which is the mass, the column density, is simply given by the integral ds times rho, and so this would be simply the total distance of this thing will be s. So we would basically say this is then rho times s, and so that is something that we can assume that it's homogeneous, and so we have just one number attached to this one slab, and that's basically characterizing everything else. Now let's go on with a simple model. So how far can we take this? So let's assume now we are not going to be interested now in dealing separately with carbon, nitrogen, oxygen, and let's ignore everything beyond that because they are subabundant. So basically, you see, for example, The next species which is abundant here is the neon, but that's already a factor 10 below each of these three, C and O. So let's put these three together. Let's make this no, sorry, this is a bit too much. Let's just make those three. Let's call that the medium group. And these guys here we call the light particle group. So we make life a little bit simpler here. So let's assume we do not have any light particles at the source. This is a good assumption because if we look at the stellar medium, we can say that at the source L will be essentially gone. So let's assume we have a number density Nm that we start out with. So that's produced and emitted by the source. And let's ask ourselves now what's going to be observable for us. So Nm, as a matter of fact, should be then N carbon plus N oxygen plus N nitrogen. So N could be a density, it could be also an absolute number, it doesn't really matter. Let's assume it's an absolute number of particles that we inject. Now, the light particles, so we will see then Nm after Xi, and let's see how big that value is. And we would have then Nl after Xi to be then the sum of lithium, beryllium, and bohr. So let's assume Nl for Xi equals 0, and M of is the one that we have at Xi equals 0. So let's see, we can make a very simple equation for this. So we can say the number of particles will change per path length by assuming that there's an interaction length over which the interaction takes place. Let's call that Xi-m. So there will be a minus here because we will deplete the particles which have an interaction length of Xi-m. And this will be then, if just this equation would be valid, it would be just an exponential as a solution for this. However, we also have to take into account, in principle, what we will neglect that in the following anyway, but let me just write down the term here. We will also have higher species, higher mass species, for example, neon, silicon, and so on and so forth, that would interact with the interstellar medium and they would produce this. So there would be additional particles coming, Nm, or particles of the medium group being produced through spallation of more heavier ones. And let me write that down. So that would be, for example, the probability for a heavy nucleus to do spallation to produce a nucleus of the medium mass range. And then we would have here the number of particles which are heavier than our medium mass group divided by the corresponding interaction length Xi-h. Now Xi is related to the cross-section, so the larger the cross-section, the shorter that is. This term here, however, we want to neglect. So we basically say this is roughly 0, or it's smaller than Nm. Let me put it that way. So this is much, much smaller than Nm divided by Xi-m. So this we can basically neglect this term here. So we just take it out of the equation. And then we would immediately be able to write down the solution for Nm. Nm would be simply Nm0 times e to the minus Xi divided by Xi-m. So that's simple. But while doing so, we also want to solve the equation for Nl. So let's look at the equation for Nl. That would be, again, the losses through spallation. That is, the light elements, they would also do spallation and they would produce hydrogen and helium. So there would be Nl divided by Xi-l. And we now have essentially the particles which are heavier, and the ones which we want to consider here are the medium mass group. So we would have here then a term which is medium, the probability for medium to go to light, times Nm divided by Xi-m. So these are two equations which are coupled. They are not too difficult to solve. In, for example, the long air book, you find the solution to this. But we can essentially just draw a graph to get at least now an understanding what will happen. So let's assume this is now the number of particles after some path length Xi. And Xi is not known. We don't know. We don't know how thick the slab is. We don't know the density a priori, and we don't know the geometrical distance. So let's assume Xi is just free. We don't know it. We want to infer it, as a matter of fact. Then we will have for Nm, the solution is very simple. So we start out with Nm for Xi0, and then we will have an exponential decay. So that basically after psi m, we will go down to about 1 over 3, so 1 over e of the number. And at the same time, since this will feed this term here with some losses here, so we will have here some increase of the light particles. So it could actually go even cross it through here. And we don't know now how far we are away, but now if we were able, so let me just write this down, this NL, if we are now able to measure the ratio of NM to NL, so we would fix that ratio, we would know that, for example, if it's like 0.25, and that's roughly what we get, we will be somewhere here. So then we would know what the psi is of our slab. And this is actually exactly what we do. Let me just maybe also write down so that you know how to calculate this PML and so on. So PML is given by the ratio of the partial cross sections for producing lithium, beryllium, and bohr out of an interaction of carbon, nitrogen, and oxygen with interstellar medium matter. So that would be essentially now, let's say we sum this up again. So then we would have the cross section for the light particles. Let's make it maybe I, and I would be lithium, beryllium, and boron. And then over the total cross section for the spallation. So including all other final states, including hydrogen and helium, for example. And the psi m, I should also say, for example, how you calculate this. So psi m, for example, is given by the cross section. So that's essentially just rho divided by the interstellar medium density, number density, times the cross section. So this would be the total cross section for interacting with m. And so n is the number density of the interstellar medium, and rho would be the mass density. And you can also rewrite it because number density and mass density, of course, related by the mass number and the mass of the nucleon. So we could basically now infer this rho slab by measuring it. But before we go into that, let's have a look at once more whether this these abundances that we see. Keep in mind, there's already some particular way that these abundances are grouped here. If you look at it, whether they relate maybe to the actual partial cross section to produce, for example, lithium, beryllium, and bohr. So I looked them up for you. So we've got the cross section for any of the medium elements to become a lithium. That is 24 millibarn. And for the beryllium final state, we get about 16 millibarn. And for the boron final state, we have about 35 millibarn. And that means that basically in the final state we should have roughly this ratio. So beryllium should be the least abundant. Then you should see some more lithium, and the most large abundance you would expect for the boron. And if you now look at this one, this is exactly what you have here. Okay, so this is already quite good, and this is consistent with the abundances. That we measure. So that's good. That means that our spallation assumption basically is consistent. Now we measure, let me just conclude this one to you. So the Nm over Nl that we measure is about 25%. So this is essentially, you take this graph, you just sum those three ups, and you sum those three up, and you basically see it's about a quarter of the more massive ones of the medium group. Sorry, this should be the other way around. It's not Nm, it's Nl over Nm. It's about 25%. And so you can then go to your solution, which I didn't derive here for you, but you can look it up, as I said. And then you can infer this slab distance. So this is an important number now. So it turns out this is it's slightly below 5 grams per square centimeters. So that seems to be rather small, right? But imagine you would measure a larger ratio, you would then get a larger value of this psi-s. And it also seems to be very small if you compare that, for example, with the density of our atmosphere. So our atmosphere as such, as a full column density, has more than 1,000 grams per square centimeters. And for a nucleus, a cosmic ray particle passing through this slab, it will be, even though it's several light years, it will only pass through something like 5 grams per square centimeters. Let's now make a rough estimate, assuming that the cosmic ray particle would be basically just traveling in the galactic disk and not going outside of the disk. Then we would say in the disk, the number density of the interstellar medium is about 1 per cubic centimeter. So it's easy to remember. And so how much does that mean in terms of the path length? Because we said, remember, we said S would be then, if we go back to the way that the psi is defined. So psi was defined as rho times S. So we know rho because we know it's roughly 1 hydrogen per cubic centimeter. We know the psi to be 5 grams per square centimeters. So let's have a look how large S is. And actually S turns out to be, so that would be psi over rho. And that's of the order of about 1 megaparsec. So 1 megaparsec means 10 to the 6 parsecs. And 1 parsec, for those of you who don't have maybe any deeper astrophysics or haven't taken any astrophysics courses, 1 parsec is essentially a distance scale which comes from the fact that an object or a star which is about 1 parsec away, we would see as going through the motion of about 1 arc second in the sky because of the motion of the Earth around the Sun. So that's 1 arc second per year that we see this moving in the sky, and that corresponds to about 3 light years. That's 3.08 times 10 to the 18 centimeters. And just to put that in perspective, our galaxy, to have a very simple model of our galaxy, maybe I just draw one here. So our galaxy is about this thick. That's the galactic disk, and it has a diameter of about 30 kiloparsecs, and has a thickness of sort of 100 parsec or so. So that means that if the cosmic ray particles travel for a megaparsec distance, this is a much larger distance that they travel than the dimension of the galaxy. This means that the particles must be confined to the galaxy, so they do not just travel freely and then just basically leave it after a path length of up to maybe tens of kiloparsecs, but they basically have to be going around and around and around several times, because this is much, much larger than the dimension of the galaxy. Now there's two sort of, let's say, ways that people have been looking at this data and then come up with some suggestion how to model it. So the one is the Adhoc Assumption, which is so-called the leaky box. You find this in the literature still floating around, this term, and it has some simplifications. It has some let's say good points to it. So the leaky box is essentially similar to our one slab model in unphysical assumption. So we cannot just have a slab, as I said, because the particles would basically, depending upon the distance of the source towards us, they would just pass several different distances of the slab, and this would be then the average would be 5 grams per square centimeters. However, since the slab must be bigger than the galaxy, this cannot work. So the next way that people have been looking at this, when you go from the one slab model, so maybe I'll just put this here. So the one slab model does not work, obviously, because galaxy is much bigger than the slab. Sorry, the galaxy is much, much smaller than the slab would have to be. So the leaky box essentially assumes that the particles move freely, and however, they are confined to a box. So the moment they hit the boundary of the box, they get reflected, and then they basically bounce around in this box until they have a small probability to leave the galaxy. So each reflection has a probability of whatever, very close to unity, but if it goes through several of these reflections, at some point they will leak out. So this is sort of the next step of a one slab model, but they're both unphysical because our galaxy doesn't really have a boundary where things could deflect off. So they're sort of ad hoc models, but they help to put some kind of model into perspective. Now, the more physical approach is to say that we have a diffusion zone and maybe also some convection of cosmic rays in the galaxy, and the cosmic rays, they would not bounce around, but they would basically move like, for example, as you know, a gas when it expands, or when you have something expanding or moving in our system, like in the atmosphere, you find that this moves diffusively, or if you think about charge carriers moving in solid states and so on, this is a diffusion process mostly. So a diffusion process requires, however, that the mean free path length must be very small. And this is something we will discuss a little bit later. But the process would be such that the sources inject cosmic rays and they would move diffusively. And in some regions where you have some bulk motion of the interstellar medium, you would also have some convection maybe, but mostly is moving through diffusion. And then you would essentially, if you start diffusing out of the galaxy, at some point out of the galaxy, these particles would become free and they would not diffuse anymore. So there would be some free escape at boundary. Okay, and that's sort of the most physical model that people are using these days. Now, let's talk a little bit about this diffusion process, so to understand what the characteristics are. And let me just remind you about diffusion as you have learned it in physics in your bachelor's time. So diffusion has this funny mechanism, whereas the particles are bound in a medium in a way that they basically have a very short path length, and then they bounce back and forth. So since they bounce in a random way, the average distance they travel is zero, because they get scattered backwards and forwards, so they don't really have an average displacement. But the average distance squared that a particle will diffuse out from, let's say, some central point, increases. So imagine you start out with a singular particle distribution, and after some time later, the particle distribution would spread out in space. It will still have on average the position 0, but the squared value will be non-zero, and this will basically diffuse out like this, and so on and so forth. So it will basically smear out. And this is what happens. So diffusion has this property that r squared goes with d times t, where d is the so-called diffusion constant. It has the properties of square centimeters or length squared over time. And the diffusion coefficient has also a physical meaning because it's tied to the mean free path length. So d is given by the mean free path length lambda between two scattering points times the velocity with which the particle moves around divided by 3. So we have to think about what could be the mean free path length in the case of a collisionless particle. In our case, the only thing which happens to cause a deflection of the cosmic rays is the magnetic field. So we don't know the magnetic field, but we can assume that this is the dominating or the smallest path over which a deflection occurs, given that there's no collisions over galactic scales. So what we therefore assume is that lambda is the mean free path, which in the case of diffusion corresponds to the path distance over which the particle gets deflected substantially. And so we assume this is equal or similar equal to the gyro radius. And how big is the gyro radius? Let's write that down for a moment here. So the gyro radius is given by the momentum perpendicular to the B field divided by the charge divided by the magnetic field. And as an example, we can say, or as a number so that you have an idea how big that is. So the gyro radius is about 0.1 parsecs for charge equals 1, so that shall be the charge number of the particle, times for an energy of the particle. I write this now in energy, not the momentum, but they're equal for any realistic purposes of energies that we're looking at, for 10 to the 14 electron volts. And for a magnetic field of 1 microgauss. So 1 Gauss is 10 to the minus 4 Tesla, so this would be 10 to the minus 10 Tesla. But in astrophysics, we often use the Gaussian system, so that's why I also use it here. So this is obviously much, much smaller than the collision length scale for 1 particle per cubic centimeter. So that's really, really much, much shorter, and therefore this is the one which is the most important. So let's see how that basically tells us about particle densities as a function of time. So there we have this well-known law that came up by this Dr. Fick. He basically said that a current of particles, a current density of particles, is proportional to the gradient of the particle number density, and it goes with minus d, so diffusion coefficient again. And also if you have mass conservation, so this is the mass density and also the number density, and this is the flux density. So mass conservation, or particle conservation, I should say, not mass, it's really particle conservation, but okay, they are equivalent, of course. So particles do not get destroyed. So you got dn over dt is equal to minus gradient of j, or divergence of j. And if you combine these two, you basically get an equation which says dn over dt. So basically now I replace the number density, or the flow density, with minus d gradient of n. So dn over dt is then divergence of d times gradient of n. And this is in the case that you do not have any particle losses. We know that there's particle losses, there's losses due to spallation, and there's maybe other losses that we have to consider. So the full equation that you can write down, I just put it here. So if psi is the number density, I took this equation straight from the 2007 review article. So that's the number density, which is a function of the spatial coordinate r, as a function of the form momentum p, and as a function of time. Then you find this is the term that we just looked at. So that's dxx is the spatial diffusion coefficient. Note it's written here with 2 indices. So basically you can also allow this to be anisotropic. So this could be depending upon the direction, and this is very likely the case if you have structured magnetic field. So this diffusion. And then we have here convection. I didn't go through that before, but convection basically means the medium has a bulk velocity of v. The q, which is put in here, that's the source function. So that would be anything which creates cosmic rays, accelerates cosmic rays. Then we've got another term here which has this dpp in it, and that's similar to spatial diffusion. You also have diffusion in momentum space. So that could be any processes which lead to acceleration or reacceleration of cosmic rays. So that's diffusion in momentum space. And then we've got terms here which are also continuous. So you basically have a continuous energy loss term. Could actually also be a energy gain term. So P dot could be positive or negative. And then you've got one more term which has to do with, again, with the bulk velocity, and that's basically adiabatic losses. So you have to lose some internal energy when you expand the material. And then we've got here two terms which look very similar to what we had before, but instead of psi, we have the time here, because this is now written down as a function of the time. And so we've got one which has to do with fission, so spallation. This basically removes particles with some time constant, and this one also removes particle. That's basically a radiative decay. So that's actually the equation which describes the whole process of cosmic ray propagating in our galaxy, and you can solve this equation, albeit only numerically. There's not really a simple way to do it. And the physics that you have to put in can be quite complex, in a sense that the diffusion coefficient, for example, is not a number that you can basically write down the way I did it now, because it depends upon the B field structure. So the diffusion coefficient is actually quite a complicated function. It could be also anisotropic, as I said. Energy losses, for example, continuous energy losses do not play a big role for the hadronic component, because they basically always do first any kind of fission or processes. Adiabatic losses only play a role if you have a rapid expansion. So this is usually not so important. And also convection terms, they sort of compete here with the diffusion terms. But for energetic particles, it's the diffusion term which dominates, because the diffusion coefficient is usually energy dependent and will grow with energy with some power, and whereas the velocity is just something which is a constant term. So this will be dominating at large energies. This will be for small energies relevant, and this is not relevant. So, and also the diffusion in momentum space is often enough neglected because it doesn't really play an important role. And so you can bring this equation in a simpler form, and then you can solve it also in the way that we discussed it. Now, after we looked at this equation, which is tough to solve, but we're not going to attempt to solve it, but we can still, as I said, use some of the very simplified models to get an understanding of what's happening. Now let's look at the data. What does the data tell us? So one thing that we can infer from this equation is you do this solution for the heavy particles and for the light particles. And you can basically do the same thing as we did in the slab model, a bit more sophisticated. And then you can predict secondary to primary ratio, like for example boron to carbon, which are the most abundant ones that you find. So this turns out to be of energy dependent, so it's not a constant number. The number I quoted before, 0.25, is again the integrated number, integrating over the whole energy range, and also taking the three light species in a summed and combined way. However, what you usually find in the literature is the boron to carbon ratio, because that's the one which is having the largest value. And so here I give you now something which is a couple of years old now. That's a summary of this measurement. And you find the measurements that I quote here are the ones from the AMS experiment. So that's the gray points which you find here all along. And also the Pamela data. It's called preliminary data because 2015 that was just preliminary data. But I like this figure because it has also some models in it. And now let's look first at the qualitative way that this ratio looks like. So you find that in the beginning it starts rising. So the models start rising, I have to say. There is actually some measurements which go to the smaller values, which are below a GeV per nucleus. And there you find that they turn down again. This is not so easy to see, but the data really supports this. And the model calculations also predict this because, as I said, advection becomes dominant. That is, there is a flow of matter, if there's a galactic wind driven. So interstellar medium, because of dynamical effects, like for example supernova explosions or stellar winds, tends to drive a wind where interstellar medium is basically driven out of the galaxy. It's not necessarily driven out with the escape velocity of the galaxy, so it would never come back, but it's more like a fountain where the particles get blown out, or the interstellar medium gets blown out, and then basically at some point it falls back. However, this advective motion leads to some depletion of cosmic rays at low energies. That's why you see some drop off there. However, let's look at the energy dependence beyond that peak. There you find that the data follows pretty much a power law. So note this is a linear scale on the y-axis. So this gives you the value of B over C. And there's a logarithmic scale on the x-axis. So a pure power law basically looks like some of these lines which are indicated here. And you find there's three models given here. I don't want to go into the details. But they do have a dominant difference, that is, they predict different energy dependencies of this diffusion coefficient that is used for this modeling. So, and this relates again to the way that the magnetic field looks like. Not particular its strength, but more its the way that it has, let's say, spatial dependence. So what you can do is you can look at the so-called power spectrum of the magnetic field energy density. And this one has then a particular power law index, which depends upon the dynamical motion of the material. Interstellar medium is a highly turbulent medium, and therefore you expect that the turbulent flow will also reflect in the power spectrum of the magnetic field. And there's two very prominent ways that this power law spectrum in the magnetic field energy would depend upon the wave number. So the one is the Kraichnan, and the other one is a Kolmogorov, and they lead again then to different energy dependence of the diffusion coefficient. And that has to do with the fact that this is not just one homogeneous B field, but the B field is basically following such a turbulent scaling law. And so depending upon the energy of the particle, or the energy of the nucleus, you will have a particular gyro radius, and if that gyro radius matches the inverse of the wave number of your power spectrum, then you have some resonant effect, which basically leads to maximum scattering of the nuclei. And this then leads to a particular way that this rigidity-dependent diffusion coefficient behaves. So there's the so-called Kraichnan power law spectrum and the Kolmogorov. Kraichnan is going in the blue line with d to the minus 1.5, whereas the Kolmogorov, it's the red line, goes with d to the 1/3. So now, if you look at the data, it's sort of not completely clear which one is favored. There's also another one which I'm not only discussing, is PD model. And it seems like that maybe the Kraichnan model is slightly better at describing the data than, for example, the Kolmogorov, which has a slightly different slope here. And so this tells us, a lot about the magnetic field structure, but this is not something I want to discuss in great detail here. But what we can basically make out that is that the diffusion coefficient increases with energy. That means that the average square distance over which the particles can travel goes up proportional to the square root of d, and therefore the particles can travel further outside of the galactic disk. And if once they start leaving the galactic disk, they do see then a smaller magnetic field, and at some point they can freely escape. So what we're seeing here in this B/C ratio is that particles with increasing energy will have a different, if you go back to the slab model, they will have different slabs over which they traverse. So there's a sort of energy dependence of the slab that is predicted through this diffusion coefficient, or energy-dependent diffusion coefficient. So one can also look at it in this very simplified way. So let's assume we basically say that we not only have the interaction, but also escape. And then we can put our little equation up again, that is the one slab model, but now we assume that the escape slab, there's a particular slab length which corresponds to the escape of particles. So then our equation basically comes back to, oops, this is not so good. So that would be then our equation for the medium particles. So we would have PML and NM over Xi m. This is the term that we had for the light particles, minus NL over Xi L. That would be the interaction losses, so spallation. And now we add another term to this. That means that NL is also depleted by escape. Let's call that Xi E. And that's supposedly now energy dependent. So even in our one slab model, we can just ad hoc say there's an energy dependent escape length. And that would be 0. And then basically, so I put it to be 0 because now we assume that things are in equilibrium. So that is not dNL over dxi, but we say it doesn't change anymore over time. So it remains constant. And if we now assume that at this part over here, obviously escape becomes dominant because you don't produce much boron anymore. So Xi escape must be much smaller than Xi, let's say L or Xi m. And this is true for above, let's say, 10 GeV. Then we can solve this equation again in the same way. We can calculate N and M, and that would be then PML. If this term basically can be neglected, then we have just this equation solving over here. So the NM and the NL, we can calculate the ratio. Then we've got PML times Xi E, which is energy dependent, divided by Xi m. And since Xi m and PML are just constants, that means that the ratio becomes energy dependent, and it would become energy dependent with some value of delta. So keep in mind, delta I put here to be -1/2 or -1/3. So it becomes shorter and shorter with increasing energy. And then we basically predict this kind of power law slope here. In the case of diffusion, you basically get the same, albeit then you basically make the diffusion coefficient energy dependent. So, but the main thing which you should bear in mind here, let me make that in thick and red, is that particles will escape, otherwise this B/C ratio and its energy dependence is not explainable. So we have escape of cosmic rays out of the galaxy. So they're not confined forever. That means we need to replenish. There must be some mechanism which basically feeds a new cosmic rays, because these ones will disappear. And that's an important conclusion to draw from this. So we don't know yet how much time the particles remain, but we know now that we have to bring back cosmic rays continuously, otherwise they will disappear over a finite timescale. And as it turns out, the timescale is actually not so long, so we may have to actually, we can give an estimate on the required energy or power, let's say, that's needed to replenish cosmic rays.